Have you ever stopped to look around and just wonder how the incredibly complex world around us is held together? I mean, every star, every ocean, the screen you're looking at right now, and even the cells in your own body are all constructed from the exact same invisible blueprints. Welcome to today's Explainer. We are going to explore the magnificent microscopic architecture that dictates the structure of our entire universe, the electronic configurations of atoms. Think of it like checking into the Grand Atomic Hotel, where the rules of occupancy are dictated by the bizarre and beautiful laws of quantum mechanics.
Okay, let's dive right into our roadmap for today. We'll start with the architecture of atoms, move on to visualizing quantum orbital shapes, decode the cosmic building codes, put it all together by constructing specific elements, and finally zoom out for a look at the periodic table map.
So, Section 1, the architecture of atoms. We're looking at the fundamental levels of atomic structure.
Nature isn't random. Far from it. At the quantum level, everything operates with just astonishing precision. Literally, every atom in the universe follows a strict architectural blueprint for how its electrons are arranged. If you imagine an atom as our grand hotel, the electrons are our guests, and, well, they can't just sleep wherever they want. They are bound by a completely foundational rulebook of reality. Starting with the absolute basics, right in the center, we've got the dense, heavy nucleus. Surrounding it are what we call energy levels, or shells. They're labeled n equals 1, n equals 2, and n equals 3. These energy levels are basically the main floors of our Grand Atomic Hotel. Electrons occupy these specific floors, and as you might guess, the further away you get from the nucleus, the higher the energy level. And there's this profound, beautifully simple law of nature governing how many guests each floor can actually hold. The maximum number of electrons in a shell is calculated by the formula 2n squared. So on floor 1, the K shell, we plug 1 into the formula and get a maximum of 2 electrons. Up on floor 2, the L shell, we can hold up to 8. And by the time we reach floor 4, the N shell, it can hold a massive 32 electrons across its various sublevels.
Moving on to Section 2, visualizing quantum orbital shapes, from spherical to complex geometries.
Remember how each floor has sublevels? You can really think of these as the distinct types of suites available on a given floor. They're designated by the letters S, P, D, and F, which historically stand for sharp, principal, diffuse, and fundamental. The S sublevel is cozy. It contains just one orbital holding 2 electrons. The P sublevel has 3 orbitals holding up to 6. The D holds up to 10, and that massive F sublevel has 7 distinct orbitals, accommodating up to 14 electrons. But here's the really cool part. These aren't just flat, circular tracks like planets orbiting a sun. No way. They are 3-dimensional probability clouds. Let's act as a virtual camera for a second and just zoom right into these beautiful blue and gold geometries. These geometries are literally a masterclass in quantum architecture. The s orbital is a perfectly symmetrical sphere. As we step up to the p orbitals, they stretch out into these dumbbell shapes, orienting themselves perfectly along the x, y, and z axes. The d orbitals transform into striking gold cloverleafs, stretching into entirely different spatial planes. And by the time we reach the f orbitals, the shapes are so highly complex they look almost like blooming alien flowers. It really is the visual majesty of the microscopic world. All right, Section 3, the cosmic building codes, the strict rules of electron placement. So the first major law of our atomic hotel is the Aufbau Principle. Simply put, electrons fill the lowest energy orbitals first. The universe is, well, inherently lazy. It always seeks the lowest possible energy state to build its foundations. You obviously can't start booking guests into the penthouse suite if the ground floor is completely empty, right? Next up is the Pauli Exclusion Principle. This dictates that no 2 electrons in an atom can have the exact same set of 4 quantum numbers. Practically speaking, this means any single orbital room can hold a maximum of 2 electrons. And to maintain harmony within that incredibly tight space, those 2 electrons must have opposite spins. Finally, we have Hund's rule. This kicks in when electrons are moving into degenerate orbitals, which is just a fancy way of saying a set of orbitals on the exact same energy level, like those 3 p orbitals we saw earlier. Hund's rule states that these orbitals fill singly with parallel spins first. Think of it like getting on a bus. Strangers are always going to choose an empty seat before they sit down right next to somebody else. Electrons want their own room before they're forced to share. Now this brings us to a fascinating little quirk in the architecture. If you follow the colorful diagonal arrows dictating the order of filling, you'll notice something weird.
Because the 3D shapes of the orbitals get so complex, the energy levels actually start to overlap. Following the arrows, you'll see that after the 3p orbital is filled, we don't go straight to 3D. We actually fill the spherical 4s orbital first. It's an energy shortcut strictly dictated by quantum mechanics. Section 4. Constructing specific elements. This is where we put the blueprint into practice. To actually visualize this stuff, chemists use a really brilliant visual shorthand called arrow notation. A spin-up arrow represents one electron. A spin-down arrow represents an electron with the opposite spin. When you see paired up and down arrows sitting together in a single box, it signifies that that specific orbital space is completely full. Watch how these rules compound when we put them into practice. Hydrogen, element 1, has just one electron sitting snugly in the 1s orbital. Simple. Carbon, element 6, fills the 1s and 2s and then places two electrons separately into the 2p orbitals. But look at oxygen, element 8. It perfectly demonstrates Hund's rule. In its 2p sublevel, it places 3 single electrons with parallel upward spins first, and only then is the 4th electron forced to pair up in that first 2p box. Building lighter elements like carbon and oxygen is one thing, but how does the rulebook handle heavier elements? What happens to the architecture when we reach a much higher atomic number? Say, element 26, iron. Iron's configuration is an absolute masterpiece of these quantum rules. It relies on a solid core of 18 electrons identical to the noble gas argon. Then, following our diagonal arrows from earlier, it strictly fills the 4s orbital with 2 electrons before finally tackling that complex 3D sublevel. It places single electrons in all 5 3D cloverleaf orbitals first, and then goes back to pair just one of them up, ending neatly in 3D 6. Finally, Section 5, the periodic table map, how macrochemistry aligns with quantum rules. Every chemist relies on the periodic table, right? But it isn't just an arbitrary list. It's a literal map of these electronic configurations. The position of an element perfectly predicts its electronic structure. The table is neatly divided into our 4 distinct sublevels. You've got the S block in blue, the P block in pink, the D block in orange, and the F block way down at the bottom in yellow. If we compare the left and right sides of the table, we see strict mathematical endings for these elemental families. Every single element in the S block on the left will have an electron configuration that ends in either S1 or S2, no exceptions. And every element in the P block on the right will end with their outermost electrons in the p orbitals, ranging from p1 all the way through to p6. So, the crucial point you should take away here is this. The outermost layer of any atom contains what we call valence electrons. Because they're on the absolute outer edge of our grand atomic hotel, they are the ones actually interacting with other atoms. These valence electrons directly determine an element's entire chemical behavior. They are the ultimate link between abstract quantum rules and the physical, tangible chemistry of the world around us. We've explored the foundational laws that dictate how the universe builds itself from the ground up, keeping everything in a perfectly stable, low-energy ground state. But it leaves us with a pretty fascinating, provocative thought to end on. If this is the strict architectural blueprint for elements in their ground state, what exactly happens when a star explodes, or a high-powered laser fires, and extreme cosmic energies force these atomic hotels to completely break the rules?